Welcome back for lesson 3.3 about tangent and normal lines. So last time we talked about some basic derivative rules, and today we're going to talk about how we can use what we know about derivatives to write equations for tangent and normal lines to curves. So let's get cooking. So we've already talked about the derivative. We know, hopefully it's been reiterated enough at this point, that the derivative of a function can be used to find the instantaneous rate of change of a function at a point. So that instantaneous rate of change of the function of the point will be the slope of the line tangent to the equation at that point. So what we're going to do today is we're going to use that to help us write equations of lines tangent to different curves. So if I have this function f of x equals 3x squared minus 2x, and I want to write the equation of the line tangent to it when x equals 2, what I can do is first I can find f of 2. So f of 2 would be 3 times 2 squared minus 2 times 2. So this would be 4 times 3 is 12 minus 4. So this would be 8. So I know that f of 2 is equal to 8. All right, now I could find f prime of x. We can use the power rule. So f prime of x, this would be 6x minus 2. And now we can also find f prime of 2, because remember, by finding f prime of 2, it can give us the slope at the point when x is equal to 2. So that'd be 12 minus 2, which is 10. So I've gathered a lot of information from a few really relatively simple things. I found f of 2, plugging 2 into the function. So what this tells me is that this graph contains the point 2, 8. If this graph contains the point 2, 8, and then I also use this to find the slope. So I have the point 2, 8, and I know that the slope of the curve at that point is 10. I can use this to write the equation of the tangent line using the point slope form of the line. So this will be y minus 8 equals 10 times x minus 2. And there it is. That's our equation of the line tangent to this curve at the point when x equals 2. All right, so as you can see, in order to write this equation of the tangent line, we really need two things. We need a point, which we can find from f of x or whatever our function is, and we need the slope, which we can find from f prime of x, which is the derivative of f. So if I want to write the equation of this line, so let's do it again. We're going to write the equation of this line, or of the line tangent to this function when x equals 1. So I have f of x. I'm going to find f prime of x because I know that I'm going to need that. This is negative 6x squared minus 6. All right, so then I can find f of 1. So f of 1 is negative 2 minus 6 is negative 8 plus 18. So this is 10. So f of 1 is 10. F prime of 1 be negative 6 minus 6, which is negative 12. So now I have the point. My point is 110. I found that from f of x by plugging 1 into the function. And then I have that my slope is equal to negative 12. I can use those two things in conjunction with each other to write my equation, point slope form. So I have y minus 10 equals negative 12 times x minus 1. And that's my equation. All right, so we can also use this to write equations of normal lines. So what a normal line is, what it means for something to be normal, something else is that it's perpendicular to the curve at that point. So if the tangent line gives us the slope of the curve, then in order to find the normal line, I would need to just write the equation for the line that's perpendicular to that tangent line. So we're going to write the equation of this normal line. So this same kind of process here. If I want to find when x equals 1, I just did this a second ago. So f of 1, we figured out f of 1 was equal to 10. F prime of 1 was equal to negative 12. So f of 1 is equal to 10. F prime of 1 equals negative 12. All right, so we just found these. And so I know that this point, or this curve, has the line 110. And at that point, the slope is equal to negative 12. So then if I want to write the equation of the normal line, I write in point slope form, I've got y minus 10. The slope would just be the opposite reciprocal of the tangent line, because that's how I can tell they're perpendicular. They have opposite reciprocal slopes. So this would be y minus 10 equals 1/12 x minus 1. And that would be my equation of my normal line. So now that we've gotten a little bit more comfortable with the derivatives, now I feel like is a good time to bring up higher order derivatives. We're going to use these a lot more in the applications of derivatives section, but I want you to become aware of the fact that there are higher order derivatives. And what a higher order derivative is when I take a derivative more than once. So these are some different notations that you might see. You have y prime is dy dx. We've talked about these. This is the first derivative. Y double prime, you might see this as d squared y dx squared. Y triple prime, you might see this as d cubed y over dx cubed y. The fourth derivative of y, y4 prime, and then so on and so forth. We kind of repeat the same kind of process. So for example, if I asked you to find d 102y over dx 102, what this would mean is I'm finding the 102nd derivative of whatever my function is. And with higher order derivatives, and we'll talk about this more when we get to the applications of these, with higher order derivatives, the second derivative, I continue to apply the same kind of concept. The second derivative is the rate of change of the first derivative. The third derivative would be the rate of change of the second derivative. The fourth is the rate of change of the third derivative, and so on and so forth. So let's take a look at an example and find a second derivative. So if I have f of x here, I can apply the power rule. F prime of x would be equal to 9x squared minus 4x plus 14. All right, I applied the power rule. This function right here, if I plugged in some value for x, would give me the rate of change of this function. So this function is the rate of change of f of x. So now I can find f double prime of x, which is the second derivative of f. I apply the power rule again. Now I'm taking the derivative of f prime of x. So I apply the power rule again, and this would be 18x minus 4. And I could keep going. I could find the third derivative of x, f triple prime of x. Again, apply the power rule, this would be 18. Then I can find the fourth derivative of x. I apply the constant rule here, and this would just be 0. And if I notice, every derivative from now on, from the fourth derivative on, would be 0, because I would be continually taking the derivative of 0. So with polynomial functions like this, whatever the highest power is, so you notice our third derivative was our last derivative that actually had a value. After that, every other derivative will be 0. So that is it for today's video. Today we talked about tangent line and normal lines and how we can write their equations based on the definition of what a derivative is. And then we also discussed higher order derivatives so that we can see that concept and be familiar with it when we start talking about applications. So I hope you guys enjoyed this video. If you have any questions, be sure to bring them to class, and I will see you in the next video. Have a fantastic day.